Let's start. So basically, this is like a bit of a introduction to how JavaScript is running under the hood in V8 or technically in the any engine, which is like for Node.js, which is V8, and for browsers, it is different. Like V8 for Chrome, then SpiderMonkey for Firefox, and Chakra for Edge. So let's start. So before we start our journey to the performance, let's have some basic facts. Why is it important? So you see, first, if you want yourself to be felt faster than your competitors, you need to be at least 20% faster than them. Oh yes. And Akami, the global leaders of CDN, they found out that if your website gives you a 2-second delay, your bounce rates increases by 103%, 103%, which is like a really big percent. Half, I mean, like the amount of the users you are having, the amount of the traffic you are having, just double it, more than double. And that amount of traffic is being like bounce rates. So that is too much. And like 0.1 second, I mean 100 millisecond is the duration in which user feels that the application is instantaneous. No feedback is required. Let's say, so if you get a user response of API in under 100 millisecond, you don't need to show the spinner or any loading feedback. And also 100 after increasing 100 millisecond, Amazon noticed that they have 1% increase in overall revenue, which was like a 1% from a billion is also a million. So yes, that does matter when we scale up. Apart from that, Google did a survey where they found out that if they make their page 2% slower, their 2% searches were like reduced, and which means 2% less ads shown, which means 2% less revenue. And Google is like mainly business with ad revenue. So before move on to the journey, I would like to add few points. The first one is, in terms of JavaScript, doing less stuff takes less time. Yes, that is true. We can all agree on that. Um, well, actually, technically, it is related to the parsing time. So if your bundle is small, let's say if it is 100 KB, browser will like be instantaneous to parse it. And if it is 10 MB, then yes, you have to spend around 2 seconds just to parse that bundle. And second thing is, if you can do it later, do it later. By this, I mean, let's say you have some piece of code which does not need to be evaluated at the current point of time. So you have to use the add function, but it is not being used at the moment. So why to parse it? Why to waste our memory? So these are the two terms, lazy parsing and eager parsing, which I'll cover in the next few slides. And okay, so also there are few challenges with JavaScript. The first one is applications are getting bigger, like AIS. There is no way we can slow it down to get big and big. We have to add pages and everything, all that. Second, you cannot buy faster computers for your clients. You see, you cannot buy faster servers. Although you can buy MacBook Airs for your clients, they would be very, very happy, definitely. And okay, so one more thing, parsing. Parsing can be like real culprit while you have big bundles. And the last point is, parsing can be like as slow as 1 MB per second. So that matters a lot. Like we have just saw that 100 millisecond could reduce our revenue by 1%. So that matters. Okay, now how V8 works. So basically, I am touching the part of V8 specifically to the Chrome browser and Node.js. Uh, so few think that JavaScript is an interpreted language, but it's not. It's a compiled language. It's just in time compiled. Before compilation, it has a pipeline, so it creates a AST, abstract syntax tree. Then that code is fed to the bytecode and the profiling data. Oh, okay, better to show the pipeline. So you have JavaScript source code, then the code is fed to the parser. The parser generates abstract syntax tree. that abstract syntax tree gives the code to the interpreter, because interpreter cannot convert your code into bytecode, so it needs the true intention of your code. And then while bytecode is running, it generates you some profiling data. And when you have enough profiling data, we'll talk about the profiling data and the optimization part in few slides, next few slides. So the key thing is there, once your functions get hot, or like you have enough profiling data to predict few things, the compiler jumps to the optimizing compiler. The code now is not being run on the bytecode, but on the optimizing compiler. And then optimized machine code is generated, and then it is being used for the further instructions. If anything goes wrong, then the red path is taken, which is de-optimizing. So general rule of thumb, if you can get anything through the optimizing compiler, it is really good. We'll see in the live code as well. So there are few things which we will be able to cover. The few things which actually, name of the optimizing compiler is turbofan. So actually, profiling data is a whole lot thing, and there are many things which okay, I'll cover it in the speculative optimization. So the first thing which V8 does for you is speculative optimization. uh, so we all know that JavaScript is hard. It is dynamic. Why it is hard? Because there is completely like, for even a single instruction to be performed, there are number of rules. Let's say you have an add function. Uh, how tough it could be? Like, just what it has to do? It has to just add two numbers. Oh no! You see, what if you provide two strings? Oh, now, well, it can concatenate those strings. But what if you pass objects? So there are, number of rules to follow for interpreter. So if you want to see those rules, these are the rules defined in the ECMAScript, what has to be done while adding. So you see, these are, too many rules to be covered. And there is one nested thing here, which is like too primitive, and too primitive has another step. So this is too primitive up. So like, just to evaluate the definition of your add function, you have to go through these many rules. But what V8 does for you, what if we made some assumptions on the past we have seen? Let's say I'm calling add function 100 times and I'm passing only integers. Why compiler has to check, oh, in future it will be string, or it can be object. It can directly generate you the optimized machine code, which can directly add you the numbers. So I think I can show you some demos with that. So let me increase the font size. This is basically the timing APIs where, um, so this is the add function, and these are the two variables which I'm going to add repeatedly. So this is the number of iterations I'm going to perform. Oh, come on. This is the number of iterations I'm going to perform. This is the start mark, and this is the end mark. So initially, let's run it without any much thinking. No, oh, let me increase my font size. Okay, node bench. So you can see, just to evaluate a million, I'm not sure what is the number. So it's 1 to 10 to the power 7. So just to add number 10 to the power 7 times, you have to give 22 milliseconds. Okay, so let's see what is happening under the hood. Trace optimization. Come on. So you can see it now took only 12 milliseconds. That could be like many different reasons. So what I'm interested in is this line where you can see this function is now compiled using turbofan, and where is that line? See this. So now turbofan has seen enough data, and now V8 has gone for like, he knows now that you have like lot of integers coming, so he can predict like, oh, I don't have to check multiple conditions. I just know that we are only going to face integers and just pass it through the optimizing compiler. But now let's say if I do thing like this, where now in middle of some iterations I have given two strings. Now what happens? Let's see. Node hyphen hyphen trace hyphen hyphen trace d opt. So this function now tells, oh wait, I think I can grab add, which will be better. So now, so we now see that it first it marked that yes, add can be optimized, then it optimized in the next call, then now it saw that, oh no, we have to encounter strings as well, so it went for de-optimizing it, and then again the same story. So but just by adding that two strings, we have now increased our running time just from 12 millisecond to 57 milliseconds. If we go to the assumption that let's say for 10 to power 7 iterations took 12 milliseconds, just doubling the amount of the iteration should not take more than 24 millisecond, but it took 57 millisecond, around 60 millisecond, which is like a real cost. So these are the few things. Also, I think we can see, okay, now this, you might see this line where I am marking that I am saying V8 to never optimize function add. Now let's again try adding two numbers 10 to power 7 times. This is no very special thing, so we have to use this allow native syntax, and voila. Now the time increased to 209 milliseconds, just from 12 milliseconds to 209 milliseconds. And if you do not give V8 enough data or enough profiling things, you can like get in real pain. So these are the few things. So the key thing here is that we need to be consistent while passing the data types to the functions. And one more thing I think I have to cover. Just give me a second. Where is that? Oh no, yes. It's fine. Dynamic lookups. Yes. This is the second thing which V8 helps you with. So we all know that JavaScript objects are essentially the hash maps, right? And accessing properties through them is the pretty common use case. But what happens if keys are on prototype? Like you have to traverse to the object, then climb up the prototype chain, and then if prototype is also inheriting another object, then you have to climb it all the way up. What if key has been deleted? So there are so many cases. To cover up with these things, V8 gives us an internal hidden classes concept, which V8 calls map. And second thing which V8 helps us with this inline caching. So okay, let me show you first some demo with that. Okay, so this is the code where now I have reduced the iteration to 10 to power 5 times. Now what I'm trying is that I'm making a class where in constructor I'm setting this dot x and this dot y just to make an object. And what I'm doing is that running that same function 10 to power 5 times. So let's see node shapes. Oh, this took 538 milliseconds. Okay, makes sense. But what if I move this class outside of this run function? Oh, sorry. Now it took 11 milliseconds, straight from 500 to 11. Now, what could be the culprit here? Is it the class? Like just moving class from inside run to outside of the scope? Why this half second, I mean like 500 millisecond is a notable time where like user can detect, yes, there is something happening. What could be the reason? Definitely it's not the parsing. Like one could argue that class is being parsed every time when it is inside the run function, but no, it's definitely not the case. The thing is the shapes object. So I think first I can show you the shapes object. Where is my, yeah. So this is the shape object which V8 uses internally to remember your object keys. So when you, let's say you have created a blank object, you added a property X, given its value 5 and then 6. So JavaScript object is separate, the shapes are separate. So if you all know, might you all know that JavaScript object keys are not the only thing which points to the value. They also point to the three other things, which are writable, enumerable, configurable things, which tells that this shape can be enumerated, or can be modified, or can be deleted. If let's say you are creating 1,000 objects, so V8 doesn't have to like remember all these things. It will be just like duplicating all your data for no reason. Who remembers modifying their writable property, enumerable property, or configurable property in the production code? So V8 what does it that for similar shapes of object, it only creates a single map. No different maps are created. I think I can show you a demonstration of that as well. Let's say if I, so this is another V8 realm flag which tells you that the shapes which V8 internally is using are the same or not. Let's say for now I have created test outside of the run function. So now I think I can do this. So let's see if those are internally same shape or not. Shapes.js. Oh yes, they are same shapes, even though I have created different objects. So if I say console.log is a equal b, we all know that they are not. They are not equal. Yes, but the shapes which are being internally used, same. And this is the key reason why we jumped from 500 milliseconds to 12 milliseconds, even though it was like 10 to power 5 iterations only. But if I move this inside the run function, suddenly it got false. And see, same 577 milliseconds. So the key thing is here that if V8 sees that you are using the shape, internally it creates a global shape object which is empty and start adding property to it. It's like a tree iteration. So V8 only uses same internal maps if it sees that same path has been followed to the end object. So where is the, so let's say I added X and Y. If I may have took different paths, like I would have not said that, oh no, O dot X is 5, O dot Y, I would have like made this on a single line using the object literal. Then V8 would have made different object. And this is the like few things which we see in the live code and the production code. Uh, so key thing here to note is that, oh sorry, if you are using objects, make them define in the same manner so that we can optimize, V8 can optimize it for you. V8 gives you this thing for free, so leverage that. And what was the last thing? Oh yes, there are three terms which V8 or I mean every engine use internally. Things are like, the first thing is monomorphic. So if all the shapes are same, V8 can get you incredibly fast. Like, he knows all the thing, he knows where all the keys are stored. It uses inline caching for that, and it can give you fast results, which you just saw. Polymorphic things. Polymorphic things are like, oh, we have these shapes are lookalikes but not the same, so I could apply few optimization to this, another few to this, and I can get you things pretty fast, but not as fast as monomorphic. In case of megamorphic, oh no, I'm not specialized at all. Just follow the spec rules, follow the books, and go slow. So I think I can give you a good example of this thing, ECMA 262. Yes. So what I'm going to show you is the definition of object.keys. This is the pretty common use case we use in our Ascent object.keys definition. So, okay, JavaScript objects come under the ordinary and exotic objects. Don't go over the names, they are like uh, ordinary objects and internal methods. Where is that property? Oh, own property key. So internally, specs do not say it like, oh, it's object.keys. They say the internal names, which are object.property keys. And just to find out the keys inside your any hash map, it has to go these 5 steps. Like, oh, create an empty list, then what are the integers in it, give them in ascending order. If they are string type, follow the path which in they were added. If they are symbol, follow the path in which they were added. And this is the key thing which slows down your object.keys. So these are the few things which I come up with for object.keys, and they are like, this is 8 to 900 thing, 900 pages spec, so I'm not going to cover it all. Yeah. Conclusions. So this is the main thing which I wanted to talk about. Optimizing compiler is slow. Why? So we know why. Because it needs some information from you or from the bytecode or profiling data. So while it is booting up, it's our duty to make things fast. But once the thing are went into like optimizing compiler, things are out of your hand. And if, which is good actually, which is good. So V8 can get you things pretty quick. We all saw that from 11 seconds to 200 milliseconds is like real pain. And it needs too much of information. Like, it does not optimize you a function for like 2 or 3 calls. You need to like have few hundred calls before it gets optimized. And the third thing which actually helps us in our code, either use a type system or prop types in Ascent to make things fast. If we have proper or consistent prop types, we can get browser things really fast, because apart from Node.js, browsers are way more optimizing your JavaScript in the wild, because they have seen more code, more profiling data, more caching, and a whole lot more memory as compared to your server.